We looked at interpreting endpoints of observational studies. Now, let's determine the type and strength of correlation between two variables, which is the course learning outcome number 4 on the course syllabus. When it comes to clinical studies, clinicians are interested in 3 sorts of questions. We want to know if there is a relationship among different measures or variables. And for that, we look into correlation. We also want to know if we can predict individuals at high risk of having a subsequent event. And for this, we look at predictions. And of course, we're interested to know if there's a causal relationships among biologic phenomena. And for this, we look at causation. Correlation is the degree of association among different variables. Now, if we want to describe the relationship among different variables and predict value of a variable based on another variable's value, we use a technique called regression. Let's take a look at correlation first. Correlation is essentially a statistical tool that allows us to see if there's a relationship between two variables. For linear correlation, we typically use the Pearson correlation, and for nonlinear correlation, we use the Spearman correlation. When there is a correlation between two variables, this correlation can be positive or negative. In a positive correlation, both variables move in the same direction, whereas in negative correlation, they move in inversely in different directions. Clinically, we are interested in strong correlations, whether it's a strong positive or a strong negative correlation. Let's take a look at Pearson correlation as an example. While Pearson and Spearman correlations are calculated differently, clinically, we interpret them similarly. So I'm only going to talk about Pearson correlation here. What you need to look for is the Pearson correlation coefficient, which is typically represented with the letter R. And R can range from negative 1.0 to positive 1.0. And of course, a negative 1.0 would mean a perfect negative correlation or relationship, and positive 1.0 means a perfect positive correlation. Now, while there is no guideline to determine at what value the correlation would be a strong correlation, clinically, commonly a 0.8 is accepted as a threshold. So anything, so on the negative side, anything that's between negative 0.8 and negative 1 is considered strong negative linear relationship, and on the other side, positive 0.8 to positive 1 is a strong positive linear relationship. And of course, 0 would mean no relationship. Now, you have to use your clinical judgment. So if it's something negative 0.7, depending on the situation, you may consider it strong relationship. Whereas if it's negative 0.2, because negative 0.2 is closer to 0, it may not be clinically significant. But these are the numbers that, at least in JAMA, it's the JAMA's users guides is recommended. Now, while R will tell you, how strong the correlation is between two variables, you also need to know if it's statistically significant. So we also get the p-value for the correlation. So for this p-value specifically, the null hypothesis is that there, the correlation between the two variables is 0, or basically there is no correlation between the two variables. So if the p-value is significant, we will reject the null hypothesis and then accept that there actually is a relationship. In other words, if the R happens to be 0.2, while we can say that there is a weak correlation, the question is that correlation a true weak correlation, or is it due to chance? And that's why we need the p-value to know if that correlation is due to chance or is it statistically significant. Alternatively, we can also get the confidence interval for the R. So if R of 0 means no difference and we get the confidence interval, so that confidence interval should not include 0 in order to be statistically significant. And the stronger the correlation, the more likely that the p-value will be significant. And also, in addition, a larger sample size will be more likely to have a significant p-value for a correlation. Another concept that's clinically important is the concept of coefficient of determination, which is basically calculated by squaring the r. So because we're squaring the r, we can no longer have a negative number. So the range is from 0 to +1. And although there is no guideline, on interpreting the r squared, a commonly accepted threshold is if the r squared is greater than 50%, this coefficient is extremely useful, whereas if it's less than 10%, it's not very helpful. So usually we want to see an r square of at least 50%, which kind of goes along with, if you want your r to be 0.8, if you want the r to be 0.8 to be a strong correlation, then the r square would be, so maybe I should say at least 0.8 would be good. Then the r square would be at least 0.64. Now to make things easier, we're going with 50. So an r squared of at least 50 is extremely useful. 50%. So this 0.64 is 64%. Now, before I show you an example, let me orient you to some pharmacokinetic concepts so that you would understand the example. So here in this picture, we're looking on the x-axis. We have time in hours, so 0 and then 24 hours, 48 hours, 72, and 96. And on the y-axis, we have concentration of a drug in the blood. So you can see, at time 0, the concentration in the blood is 0. Now, at some point, we're gonna infuse this drug intravenously into the blood. So as we start the infusion, the concentration in the blood goes up. So let's say we infuse this for 1 hour. So after 1 hour, we stop the infusion. So we have infused all of the drug. So now we have a concept of Cmax, which is the maximum concentration of the drug in the blood. And sometimes we call this a peak drug concentration. And because we stop the infusion, now the body starts clearing it. Now, assuming one compartment model, the body will start to clear this drug. So the concentration as time goes on, the concentration starts to go down until it's time for the next infusion. So at this point, 24 hours later, we're gonna give another dose. So now the concentration starts to go up until let's say we infuse it for 1 hour. So you get another peak level, and then the body starts to clear it until it's time for the next dose, so on and so forth. And then, so the concentration right before we give the next dose, that's the lowest the concentration would go. And we call that the Cmin, or the minimum concentration, or sometimes we call it a trough drug concentration. Now, another thing that we can do is the concept of area under the concentration time curve. So which would be like calculating this area under this graph. And so this shaded area is the AUC for 1 dose. If you want to calculate for 2 doses, it will be all of this area as well. So now that we know what's a peak, what's a trough, and what's a AUC, or area under the concentration time curve, let's look at an example. So in this study, vancomycin is an antibiotic. So they were looking to see if there's a correlation between vancomycin trough levels to AUC. So on the x-axis, they are showing you the different vancomycin troughs, and on the AUC, they're showing you the area under the concentration curve. So and these are all the this is a scatter plot of all the values that they got in the study, and then they want to see if there's a correlation between trough and between AUC. So you can see they calculated the R to be 0.437 or 43%. So there's a 43, or let's round it to 44. There's a 44% correlation between vancomycin trough levels and AUC. And as you recall, we were interested in a value of 0.8 to call it a strong correlation. So this is not a strong correlation. In fact, it's worse than a coin flip. So it's not even 50%. Now, if you look at the p-value, you can see that, while the correlation is not strong, but it is statistically significant. So you can say that there is a significant, and by significant we mean statistically significant, correlation between the trough and AUC of vancomycin. Now, if you square this, so if you get R squared, you get the coefficient of determination, which becomes 19%. And as you remember, we wanted a value of 50% for it to be extremely useful. And what this means is that, the variability in AUC, or I should say, because the R squared is 19, I can say that 19% of the variability in AUC is explained by the vancomycin trough levels. And that's not very useful because this 19% is very, very low.